started. Welcome to the last first session after lunch of CCC 2023. The first talk is going to be given by Tommaso and about refutations of random CSPs. So,
thanks a lot. Can you hear me well? Yeah, okay, good. So yeah, the title is long. So this is what we look at, by the way. So the title is long, and I was talking with Anupam Gupta the other day, and he told me, oh, I ran into this paper. I read two names that I don't know, meaning Yar and Bas, not. And so I got discouraged. So yeah, we can just call it a strong refutation for random CSPs, as it was announced. So what is this about? It's about refuting CSPs. I want to consider a particular one for the scope of the talk, which is going to be 3XOR. This captures all the algorithmic phenomena and difficulties that we are interested in here. Okay, so how can you reason about 3XOR? So I want to construct an instance with n variables and m clauses. I'm using this parameter p to denote the clause density. Okay, so I have like roughly n cube clauses, so the number of clauses m will be roughly n cube times p. And a way to generate a random 3XOR instance is by sampling a random tensor. So I'm using boldface for random variables, so you can keep track of what is random and what is not, unless I forgot to make it boldface. And so you can sample such a tensor by you look at the entries and you set it to 1 with probability p over 2, minus 1 with probability p over 2 again, and 0 otherwise. Okay, good. And now, if you give me an assignment, which is just a plus minus 1 vector, then its value is essentially 1/2 plus the product between the tensor of x and the tensor t. Okay, so here I'm normalizing by the number of clauses. So this is how I want to reason about random CSPs. Okay, and now what is the objective I'm interested in is finding, or at least thinking about the choice of x that maximize the number of predicates that are satisfied. Okay, so this is going to be this opti maximizes this tensor norm here. Okay, so and in particular, I want to reason about refutations. So what is a refutation in this context? It's a certificate, it's a proof that the maximum over all vertices in the vertices of the hypercube is a fraction of m. Okay, so I can only satisfy epsilon fraction of the clauses. And a refutation algorithm, let's say epsilon refutation algorithm, is an algorithm that either fails or tells me that only a fraction 1 minus epsilon of the clauses can be satisfied. And it should fail with low probability, so it should be useful. And in particular, it should never tell me, oh, you can only satisfy fraction 1 minus epsilon. Well, that is not true. So my goal here is to design an algorithm that provide this kind of strong refutations. Okay. So what is the result? So what is known is the following. I'm condensing a lot of work, in particular in one paper by Allen, O'Donnell, and Widmer, which says that you can have an efficient algorithm for epsilon refutation as long as the clause density is at least, and I'm hiding custom factors here, n to the minus 3 over 2. The 3 is for 3XOR, so you can replace that with k if we talk about KXOR and in general CSPs, over epsilon squared up to a polylog n factor. Okay, and you can guess that I wrote that in red because the improvement is that we get rid of the polylog n factor. Okay. So yeah, so the result is you have an efficient algorithm that does refutations, and it's sharp at this n to the minus k over 2. So, okay, so to at least my eyes, let's say, of algorithm designer, this looks in the context of CSPs as a modest improvement. So there is a natural question to ask, which is, why was the paper accepted? Okay, so I hope that, so you should ask the reviewers that, but I hope I can convince you that there's a good reason for that. And essentially the idea is that reasoning about these random CSPs and these tensors boils down to proving a bound on the infinity to 1 norm of a certain matrix. Okay, this matrix, it depends on the tensor, and it has complicated dependencies among the entries. Okay, so this is like the technical challenge that you need to solve if you want to, at least, it's one way in which you can get refutation algorithms. And I wrote proving here, so there's of course a question. Okay, you can show a bound, but can you like design an algorithm that certifies that bound? So it turns out that this is not hard to do, at least in the context we are talking about here. And so we can just reason about proving these things. I have a slide in the appendix in which, if we have time, I'll convince you that the problem really boils down to these kind of questions. Okay. So the contribution is in fact a bound to prove the, like a, maybe novel machinery to bound is infinity to 1 norm. So the quantity I wrote above is this infinity to 1 norm, if you're not familiar with it. Okay. So it's so I want to give you an idea of how you can get these kind of bounds. So that's my goal for the talk. And it's a bit hard to do it with CSPs, so I'm going to use a graph analogy for that. So we're going to reason about adjacency matrices of graphs. And I want to start with this toy problem. So we have a graph on n vertices. A is its adjacency matrix. The graph is random, and it's a GMP graph. Okay, so probability that you have an edge, it's d over n. So d is the expected degree. We can think of d as a constant here. Okay, so much the graph is very sparse, and edges are independent. And now I want to ask the following question. Okay, I want to bound the maximum cut of the graph. So in particular, I'm interested in, let's say, how far it is from its expected value, let's say. So there's it's an easy problem. There are many different ways to do it. I have grouped here a few. First one is, okay, I just take a union bound over all possible plus minus 1 assignments, and this works and tells me that this maximum cut is n times square root of d. Okay, up to constants. I will not be interested in getting sharp constants. So a second approach is to use the trace method. So I bound this max cut by the deviation of the spectral norm, or spectral norm of the deviation, up to scaling. And I take, let's say, a large power of this matrix and look at the trace. And this gives me a worse bound up to a polylog. And the reason is that there might be vertices of logarithmic degree or super constant degree, and this inflates the value of the spectral norm. Okay, so that's where this additional polylog comes from, and this is also you can imagine something similar is happening for CSPs. Yeah, so this is essentially what I was saying now. And there's a third common approach, which is, okay, I want to bound it with the spectral norm, but I'm going to remove vertices of I degree first. Okay, so this is in particular, I think, there's a paper by Feige and Ofek from 2005 that does that. So I truncate high degree vertices and take a union bound over this view. And this again gives me the right bound up to constants. So again, n times square root of d. Okay, cool. So let's go back to our problem. I want to bound the max cut of this graph, and I want to make it a bit more complicated now. I'm going to say, okay, the expected degree is still the same, the marginal probability of an edge is still the same, but now edges are not independent, they're only polylog n independent. I'm intentionally vague with these polylogs so that you can pick the right one that works in the proof here. Okay, so let's look at the approaches that I showed you before, and let's see what happens. If I cannot take a unit bound over the hypercube anymore because of these dependencies, so the first approach failed. I can also cannot take a unit bound over a sphere, so the third approach fails as well due to these dependencies. So what I'm left is it's a trace method. Okay, so I again take a power of this matrix and now look compute the trace. And this is tied out only up to polylogs. And why does it work? It works because it's enough to look at polylogarithmic powers. So I'm only looking at monomials of, let's say, log n variables, and so I can essentially carry out the same proof that I had in the fully independent case. But it's not tight. So I want to suggest a fourth path to prove this bounds, which is based on this Yarabas identity. So what you see here is not exactly the so-called Yarabas identity. It's something that you can derive from it fairly easily. So let me just improperly call this the Yarabas formula. And what it does, you're bounding in PSD order your matrix by a diagonal matrix. So I here is the identity, and D is the diagonal matrix in which entry I is the degree of vertex I. And there is some parameter lambda that we'll see in a second. And why is this useful? Well, if I know this, then I can bound my maximum cut just by computing the trace of this matrix. Okay, so what is lambda? Lambda is the smallest eigenvalue of the number tracking matrix associated with the graph. Okay, so there's a few things to say here. One is how you define this. So first of all, it's like a 2 times number of edges times 2 number of edges matrix. And you have an entry I if the oriented edge E followed by oriented edge F is a path in the graph. So I'm looking at paths of length 2. If I look at pair of edges, if that's a path, I vary to 1, otherwise it's 0. And I want to compute the smallest eigenvalue of that. So, okay, it's not clear that this is easier than other techniques because you need to compute this eigenvalue here. But let's look at the fully independent case to get a sense of this. And we can use ideas from previous works on, let's say, stochastic block models, random graphs. We have tools to compute these eigenvalues. And in fact, in the fully independent case, this is already done. And this tells you that lambda up to signs, say, is square root of d. So if you look at the formula and you replace lambda with square root of d, then you get something like n times lambda plus d over lambda, which is exactly n times square root of lambda. So this fourth approach gives you, again, the tight bound that you expect. And the catch is that how do you compute lambda? You use the trace method on this number tracking matrix. And now you can guess that this works also in the dependent case as well, because I only need, again, to look at monomials of polylogarithmic degree. And so this is like this fourth approach also works in a slightly more complicated case that I was talking about, and gives gives you the right upper bound of the max cut. So the message here of the talk, and I guess of the paper, is this idea that You can bound these kind of norms using the trace method on matrices that are related to the adjacency matrix, but not exactly that. Okay, so next thing I want to do is just give you an idea of how you apply that to CSPs. It's slightly more complicated technically, but you kind of saw already all the ingredients that you need. So the first thing is that this formula that I showed you only worked for graphs, or at least as originally wrote, it only works for graphs. So you need to generalize this thing for symmetric matrices in general. Okay, so that's the first thing. So you need a suitable definition of non-tracking matrix for symmetric matrices and not necessarily adjacency matrices of graphs. And when you have that, now you can like sandwich in PSD order your matrix A with two diagonal matrices, call them M1 and M2. And now you can carry out spectral analysis on these non-backtracking matrices. You again borrow from this machinery that's already there for random graphs, and you start from that. And this gives a bound on this infinity to 1 norm for symmetric matrices in general. And then you can reduce your random CSP refutation question to bound this infinity to 1 norm, and that's how you improve the result. I guess this extra thing I want to say is that this does not only work for refutations, but of random CSPs. Seems these ideas carry over also for semi-random models. So I see that I've been fast. So we have time. I have time to convince you that refuting random CSPs boils down to this bounding this norm here. And the proof is just it's essentially this. So I'm looking at my tensor T that captures my 3x instance. I'm applying Cauchy's vars on X. So this is in the second step. And now X is a plus minus 1 vector, so one of the two terms becomes just square root of n. And the other is this quadratic form over some matrix A that has entries depending on T. So you see that this matrix A has dependencies in the entries, and that's why the graph analogy makes sense. And now I just want to bound this quantity over A, and I can upper bound it by the infinity to 1 norm. So if I show bound on this infinity to 1 norm, I'm bounding the maximum assignment. And I can do this algorithmically, let's say, using sum of squares, with which I can bound this infinity to 1 norm up to constants. Can certify an upper bound to constants. So I think this is my last slide. So I stop here. And happy to answer your questions if you have.
Well, we started 5 minutes late, and you still ended 2 minutes early, so we have a lot of time for questions.
So you should have a lot of questions. So.
Is there any, did you point to me?
Yes.
Okay. Is there any evidence that this scaling of P is the optimal, like kind of on the other side? Is there a reason that it should be hard to certify?
Yeah, I think you have lower bounds for some restricted computational models. It says those models should not be able to go below that. Yes, so I think we, at least from the algorithms that we know how to use, it's pretty good evidence.
There are these graphical refutes compounds by Aaron Hilton and others. And there you also use like a polygon factor. Is it possible that you could use this to get rid of this polygon factor and try?
So that's a great question, and I guess that the answer is yes, but it's so I think this should be improved from the polylog that you lose with that kind of machinery to constant, like bonds are tied up to constants, but it might not be easy to do so. So I think, like right now, it's still something that you use on a case by case. So we haven't been able to like write statements as general as that, but I would expect it. I would expect it to work.
Other questions? All right. Let's speak again.
Thank you.